Good morning, everyone. We'll start in 1 or 2 minutes. Probably more one. All right. So, first, good morning. Uh, First, I'll start by doing an overview of what we saw next week. I'll have a few comments in some places to do. Then, after that, I suggest we move on to the very last part of the material that will be on the second exam, which, as we discussed sometime last week, I don't remember exactly on which day, will be on Monday. So, in exactly 1 week, will be the second exam on everything related to optics. Whenever we studied mirrors, lenses, the law of refraction, reflection, as well as the new part where we studied refraction and not refraction, diffraction and interference, and what we'll see today. After that, you can tell me what you think about it. I'd probably do right away today an overview of the formula sheet, have a talk of what we saw, um, not in written form, but just talk about the formulas, the more qualitative parts, what they meant. Again, some of them we have seen some time ago, some more recently, but either way, it could be good to go over them as well. So, if you would agree, we can discuss it after material, or by the way, if you'd like to, we could do this part today. So starting tomorrow as well as Wednesday, I will be available to answer your questions, do some more examples with you if you'd like us to do so. Or a few more examples, actually, a few examples. That's it. Uh, yeah. So basically, the next 2 days could be dedicated to doing having time and doing exercises if you'd like to. At least that's what I think would be the best course of action. But if you have some other input, please tell me. So while I'll do the overview of what we saw last week, again, if you have some comments, something you'd like to say, something you'd like to ask, anything, please do not hesitate to write it down in the chat. I'm always keeping an eye on it out of the corner of my eye. So please do not hesitate to write what you'd like to say in there. So last week we continued the study of light. Unlike what we have started in the first part of the semester, not as just its rays, but as a traveling electromagnetic wave. One of the consequences of this was that if we had multiple sources, such as two slits, we could have interference between these waves, which would create bright spots due to constructive interference, dark spots due to destructive interference. A few assumptions we made in this case. The slits and the screen were very far away, and since the light passing through the two slits originally came from the same source, the two of them also had the same wavelength. So we could write the conditions of constructive and destructive interference in terms of the wavelength of these waves. Then we went on to study diffraction, which was again similar. It was due to the interference of waves emitted by some sources, but instead of having only two, we had a whole lot, all located within the same slit. I'll give it some time to stabilize. So we had a single slit. We could imagine we had a bunch of sources in them. All of these emit sources, which at some places will interfere constructively. In the middle, all of them travel the same distance, so it should be constructive. We had some other satellites where it was also constructive, but not as much. And at some other places, we had destructive interference. So the same phenomenon, but with a lot of sources, which is why we give it a different name, diffraction. A comment I have to do on this, the orientation of the pattern first, which I believe you need to answer one qualitative question. So here, the width of the slit was measured vertically. Here, the pattern uh, uh, was displayed vertically. Whenever we had two slits, the separation between the two slits was also measured between the two, which we called small d vertically, and the pattern was spread out vertically as well. We can take a look at it this way also. So here we have some kind of set which is a square with which I modify its width and its height to make it look like a slit, and we shine light on it and display the pattern here on a screen. So again, here what I at least considered to be here the width of the slit will be the vertical distance, the height, and we had some kind of pattern which was spread out this way. So if you have a slit, so a horizontal slit, so that its width is measured vertically, the pattern will be spread out also vertically. We have some artifacts on the sides here. This is due to the fact that this slit, which here I consider to be a thin horizontal slit, could also be considered as a large vertical slit with this this for a width. So this is what creates the artifacts on the side. Generally, we will neglect this and focus just on the main pattern, the one that shines the brightest. So another way we can look at it just to get rid of these artifacts Is it better? All right, sorry, my bad. So yeah, I had created a new scene to display this, but I forgot to add the mic to this one. So yeah, sorry. So I'll start over. Thank you for telling me. All right, so I'll start back at the beginning. Okay, so this you can access on Leia. This is the same software I put at the start of the semester, which I used a few times to work with the simple harmonic motion, the harmonics on a rope tied at both of its ends, and a stopped and open pipe. So this is the fourth and last module, which is used to study interference and diffraction. So here I'm studying a single slit with a given width through which I send some light here with a wavelength of 650 nanometers, which is thus red here. Since I have a single slit, the pattern I observe is due to diffraction, due to the width of this single slit. So I have a very bright spot in the middle, the central peak of diffraction, and some satellites, some other bright fringes on its edges. Instead of looking at it in terms of fringe of what I would see if I were to shine light on a screen on a wall to observe the pattern, if instead I look at it in terms of the intensity of the light. Again, a curve that displays how intense the light is at some given location. I had the curve we introduced last week with the central peak of diffraction and the satellites on its edges, the tiny bright fringes. And last time we had found an equation which gave us the position of these maxima of these minima of diffraction. We did not find one to give the position of the bright fringes due to the fact that they were not exactly centered between two dark fringes, but we could at least find the width of these knowing the position of the dark fringes for which we had the equations for. And we had tried to see how the parameters affected the pattern we saw in the case of diffraction, mainly whenever we change the wavelength, whenever we change the width of the slit. So I'll start with the graph of the intensity. So if I were to decrease the width of the slit, here it is 0.01 millimeter. If I decrease it, what we see is the pattern becomes more spread out. If you remember, the position of a given bright dark fringe was in the form, at least in a small angle approximation, of y. The position was equal to the index of the fringe times L lambda over A. So since the position and the width of the slit are the inverse of each other, whenever I decrease the width, I get an increasing position. So the dark fringes goes farther and farther away from the center of the screen. Here I call at position 0. And in the other way around, if I were to increase the width of the slit, the pattern becomes more concentrated towards the center of the screen because all of the position of the minima become smaller. So they all come closer and closer together the more I increase the width of the slit. And same thing if I play around with the wavelength. So if I were to decrease the wavelength, so from our equation, the wavelength was in the numerator. So if I were to decrease it, normally positions of the dark fringes should decrease. And this is what we observe whenever the wavelength decreases. We get a change in the positions. We can also take a look at it in terms of fringes. So here, there are a lot well, they are a lot closer than they were whenever we had red earlier on. If I were to increase it once more, when I increase the wavelength, they become more spread out. Also, the color changes because the color depends on the wavelength. And if I play around with the width of the slit, if I decrease this, they keep getting farther and farther away. And if I increase it, they come closer together. So with this, we can see the effect of the parameters we introduced last time. So on today's menu, we would, we'll build upon this and combine both interference and diffraction to treat the case where we have two slits, but each with a finite width, not infinitely thin, and then treat another system in which we won't have only one or two slits, but a whole lot of them. So before we move on to this, we'd like us to go together over something we discussed earlier. Would you like us to? Well, would you have some questions before we move on to this? If they come up later on, please do not hesitate to ask them. So, what we had studied last week, we had taken a look at diffraction, which was due to the width of a given slit, which gave birth to a pattern with some bright fringes, dark fringes, which had this shape with a very large central peak of diffraction. We also taken a look at interference. With, as stated, with two slits, we had again a bunch of bright and dark fringes. Here, next, I'll show this is the very same thing as this, but just to link better with what is coming up. We have, well, this is the same thing. We'll have bright fringes and dark fringes, but as we have seen, whenever we change some parameters such as the distance between the two slits, the positions will change. So this is the very same thing, but with another set of parameters, which will make so that these fringes, which were here pretty much spread out, are much more close together. Please do not get afraid. This is the same thing as before, just a lot more compact. But this will enable me to move closer to what I had in the next slide. So whenever we have two slits of finite width, what we'll see is the combination of the two patterns. So whenever here, if I were to add a second slit instead of having a single one, still with a finite width, so we'll see the effect of it. If I increase it, what we'll see is the following. So what we had, which was a very large central bright fringe, got divided into multiple parts. I'll go back on it to make it clearer. One slit, two slits. So it got divided in smaller parts. These parts, these are the bright fringes due to interference. So basically what we have is we'll have a bunch of bright fringes due to interference, but unlike what we had first introduced, they won't shine as brightly at least not all of them. In the center, pretty much reasonably the same, but as you get further away, the intensity will decrease. We can also look at it in terms of a graph. If we go to the graph of the intensity, if I were to increase the number of slits in order to have two, what we get is a bunch of fringes. So all of these small peaks are due to interference, and they do not have the same intensity. So at the bottom left, there is sorry. At the bottom left, there is a checkbox in which I can add another curve on the graph. So if I check it, what we'll see is the amplitude of all of these peaks corresponds to what we had due to diffraction. So whenever we have two slits with a finite width, we'll have the same fringes we had whenever we study interference, but with an intensity modulated by diffraction. We'll go back on this in a few seconds, minutes actually. So to go back on it, so if I go back to this graph with the peaks very close together, if I add the effect of diffraction, their intensity change. So they don't shine as brightly as the one in the center, and this effect is due to the curve of diffraction. What can happen sometimes? As you can see, the more you move closer and closer to a dark fringe, the more the intensity drops down. If we're not lucky, there can be a time when some bright fringe, due to interference, was supposed to be exactly at this location, but it gets extinguished due to the fact that its intensity drops to zero because of diffraction. Again, we can take a look at this happening. So I'll play with the distance between the two slits. Here it is 0.3 millimeters. If I decrease it, as we discussed last week, the peaks due to interference should move towards the outside because of the position y increases whenever we decrease the distance between the two slits. And keep an eye on these two bright fringes. As I decrease the distance between the two slits, they move more towards the right. And get smaller and smaller. So this is the one that was more towards the left, and can eventually here be almost extinguished. Can I get it to be entirely gone? Well, it survived, but still, this is due to how I set up things here. But we can get it sometimes to be exactly here, and it will disappear from the pattern. So in some exercises, you will be given this type of information. You will, for instance, be told that the third, for instance, bright fringe due to interference is at the same place as the first dark fringe due to diffraction. This means that it gets here and is not visible anymore. So from this, since you know that both are in the same position, you will be able to put the two positions equal and find the parameters you need. Also, something you will be asked a few times is how many bright fringes due to interference are inside of the central peak of diffraction. For this, we'll work out the logic here. I'll put a few more just to make it a bit more interesting. So for this, what you can do, for instance, is find the value of of the index of the maximum of sorry, find the index of the bright fringe due to interference that appears here, and from there you'll be able to deduce how many there were before. For instance, if you get, let's say that this one was exactly over here, and we get, whenever we look at this position, that we have the bright fringe of order m equal 3. That means that before it we had m equal 2, m equal 1, m equals 0, and symmetrically on the other side, here we'd have m equal minus 3, we have minus 2, minus 1, 0. So whenever you are asked to find how many bright fringes there are inside of the central peak of diffraction, count how many, what is the index here. So if it is 3, you have 2 before, you have 2 on the other side, plus the 1 in the middle. So usually you have to double the number you get here and plus 1 to count for the center. It could also be that, such as in the case we have here, this fringe is not exactly extinguished. It is a bit inside of the bright fringe just to the right. So that if you were to try and find the value of m exactly at this position, you would get some non-integer value. For instance, you could get 2.8, for instance. If you get this, what this means, m is the index of the fringes we are looking at. It has to be an integer. So if when looking at the specific position you specified, if you get a non-integer position, that means you are between two fringes. So if you get, for instance, the case 2.8, this means that 3 is more towards the outside and 2 is on the inside of the position you took a look at. So same thing as before. If you get 2.8, here we have 2, 1, 0. Here, if you get minus 2.8, minus 2, minus 1, 0. This is a bit more abstract compared to what we had discussed before. So what I do today, I'll try something at the end of the material. I'll try something to do an example live. It might fail miserably, which is why I'd probably wait until the end. So if it fails, we'll call it a day. If it works, good. So we could try it later on. An example of how to work with this. But the main logic is the pattern you get is the combination of interference and diffraction. You have the same fringes of interference as before, but with their intensity modulated by diffraction. On this, in the textbook, there aren't any examples already solved. So I refer to you to the two I put in the spell book, mainly exercises 20, only A and C. B deals with the intensity, which we haven't learned to deal mathematically, and also exercise 22. So I'll try at the end, I'll try at the end of today's class, if we have time, to do one of these two. Again, it is a trial, it might fail, but we'll try if you don't mind. So that would bring us to the end of this part of the pattern created by two finite slits with a given distance between the two of them. On this part, would you have a question or a comment, something? Yes, Jonathan. Yes, of one slit. Even if you have two, three, four, yeah, you only use the width of one of these two slits. So in what I showed earlier, yeah. So what will determine the positions of these? Sorry, I didn't switch the scene. What will determine the position of these arc fringes is the width of one one of these two slits. So you do not add them together, just one of them. Mhm. Other questions? If it comes later on, please do not hesitate to write it in the chat. Uh, Otherwise, the next subject on today's menu is diffraction gratings. Although it has the word diffraction in it, it is not exactly linked to diffraction. Well, there is a link, meaning that we'll have a lot of sources, but they won't come from the fact that we will consider the width of a slit. It comes to the fact that we'll have a very large number of slits. So this is why the word diffraction is used. But then again, we won't have to deal to the width of these slits. So what happens when we deal with more than two slits? Well, let's see. We'll try it out. So I'll go back to looking at the actual fringes. So what we would see if we were to send the pattern on a wall so we can observe it. So for now, I send light again at a given wavelength. Each of the two slits has a given width, and there is some distance between the two. So what I'll do, I'll add more and more slits while keeping all of the other parameters constant. So the width of the slits will remain the same. I'll keep sending the same time of light, and I'll suppose that the distance between two adjacent slits remains the same. In reality, that would mean that I keep getting a larger and larger object to work with. So generally, when you want to show a bunch of slits on the same object, they will, as you add more, they will, if you want to add more, they will tend to be more closer together. But here we're supposed to illustrate better what we want to see, that the distance is the same. So here I have two slits. So I get fringes due to interference with their density modulated by diffraction. I'll add a third one. So what we got? We got some other tiny bright fringes between those we had before. If I rewind a bit, keep an eye on the position of these compared keep an eye on the larger bright fringes compared to the one we had before. They are centered around the same place. We just made them thinner and added an additional bright fringe between the two of them. If I add another slit, instead of having three, I had four. I now have two tiny bright fringes between those we had originally. If I have five slits, three. And they get dimmer and dimmer the more I add slits. If I get to 6, 7, 8, 9, 10, and so on, the more I add, the more we can only see those at the position we had before, which become thinner and thinner because I keep adding more more small dimmer bright fringes between them. If we take a look at it from the viewpoints of the intensity, so I'll do the same analysis but with the graph of the intensity. So this is what we start with: some pattern with only 2 slits. If I had the third slit, we get smaller bright fringes between those we had before. Another whenever I add a slit, and another and another. And you can see that when you compare the intensity of these bright fringes compared to these, the difference become larger and larger. Also keep an eye on the y-axis, which indicates the intensity. Again, if I go back in time to 2, here I started, this was about 4 something, just 4 to compare to some reference intensity. And if I keep increasing the number of slits, the intensity of the bright fringes we had before skyrockets. It gets keeping bigger and bigger. In comparison, these don't grow at all, so they keep getting less and less visible compared to the other one. To simplify the analysis, in what follows, we will neglect what we called diffraction before, so we will neglect the effect of the width of the slits we are working with. To make it easier, just put it down as much as possible. So do as if all of these bright fringes, all those that all of the brightest ones have the same intensity. So we'll go back to the same thing we had at the beginning of chapter 35, where we studied infinitely thin slits. We had a pattern in which all the bright fringes had the same intensity. We'll do as if we had the same thing here to simplify the analysis. So we'll give a name to the bright fringes depending of how they displayed here. The very brightest ones, so these, we'll call the principal maxima, and these, the dimmer ones, we'll call the secondary maxima. And they do not have the same origin, which is why they do not appear the same whenever we display them on a screen. I'll go back to the presentation. So here I put the same graph we had before, except I did not put in the effect of diffraction so that all of these have the same intensity, so they do not have the intensity modulated by some diffraction. Here I put a total of 5 slits to create this graph, so I have 3 secondary minima in the middle. Remember, whenever we had 3 slits, 1 single secondary minimum, 4 slits, we had 2, 5 slits, 3. It increases by 1, but with a delay of 2. So the principal maxima are the brightest fringes, secondary are those that shine a little bit less, and they have a different origin. Whenever we have, here I plotted again another graph, but instead of having 5, I had 20 slits. So these you almost cannot see anymore, the secondary minima. The principal ones come from the fact that the light that came from all of the slits of our system, every single one of them, without exception, interfered constructively. So these, the more you increase the number of slits, you get brighter and brighter and brighter because you keep adding sources which will all interfere constructively at their position. In contrast to this, The secondary minima, which you cannot say anymore already with only 20 slits, which is not a lot, come from the fact that only some of these slits interfered constructively. The other interfered destructively, canceled each other. But what came out of all of this bundle of interference was only about two or three slits interfering constructively together. 2 compared to 20 is already quite a big difference, which is why you see a big difference in the interference between, in the intensity between this and this here. So if you want to have another figure that illustrates how the intensity changes whenever we increase the number of slits, I refer to you to the figure 35.15 of your textbook. Also, another point to see is these. So here, whenever I plotted the graph, I had the same the same x-axis. As you increase the number of slits, the width of the bright fringes get smaller and smaller, so they get a lot thinner. Here with 20, there is already a huge difference compared to when we had on only 5. So we had a much larger bright fringe with 5 slits than we had with 20. And so the more we add slits, the dimmer the secondary maxima become compared to the principal ones. If instead of having 5 or 20 slits, we have 1,000 or 10,000 slits, the only thing we'll see are the principal maxima. The rest, although we would be supposed to have some bright fringes, will be all but invisible from our point of view. So whenever we'll study diffraction gratings, which will be the name we'll give to a system in which we'll have a very, very large number of slits, we'll only consider the principal maxima and completely neglect the secondary ones. Now the thing is, if for the principal maximum of intensity, all of the slits interfere constructively, well, if all of them interfere constructively, that means that two adjacent slits interfered constructively. If they did not all of the slits would have interfered. So if we go back to this, what it means to have two adjacent slits interfering constructively, we'll focus on these two at the top. So here what I have is the same setup I introduced whenever we studied only two slits interfering together. I'm looking at some location on the screen. I'm looking at some ray of light that starts at one slit, goes here. Here I put a break because I'll have very large distance between the two. Goes here towards the point. The second one starts here. The second line, third line, fourth line, fifth line. So if I look at the top two, in a grating, we'll generally consider all slits to be evenly spaced. So that here I'll have a distance d between these two, d between these two, d between these two, d between these two, and so on until I reach the end of my system. Again, I'll define the horizontal with an angle theta. As discussed before, these eventually cross, but if it takes a very long distance for them to cross, we'll take them as being approximately parallel. If they were parallel, they would never cross, but if it takes a long time, they're not so far from being parallel. We'll again have the same angle theta here. By trigonometry, we found that we had again the angle theta here, and this small distance was the distance that this wave that started here and traveled up to this point traveled more than the other, which started closer. So this wave started here, went here, and the difference between the two, which was the path difference, was this distance. Well, this is the very same setup we had when we had only two slits. So for the position of the principal maxima in the case of a diffraction grating, we'll be able to use the exact same equations and the exact same logic we used whenever we had only two slits instead of 1,000, because of the principle that all of them have to interfere constructively. So again, for this to be a bright fringe, the path difference has to respect the condition of constructive interference. So this condition is still valid. Through geometry, we had found a relation between L, the distance between the slit and the screen, Y, the position of this location, and the angle theta. Math did not break over the weekend, so this is still valid as well. And if the distance here was very large, the expression we had found that the sine of theta was equal to delta over d is again still valid. So using these two equations, which we already found for only two slits, we'll be able to find the location of the principal bright fringes due to diffraction grating. So if the distance between two slits remains the same compared when we had only two, as we illustrated here, the location of the bright fringes, whenever we increase number of slits, stays the same. They are always created at the same place. But as discussed, if we want to show a very large number of slits inside of a tiny, tiny object, they will tend to be very close together. So in general, whenever we'll have a diffraction grating, we'll tend to have a very small distance, so very small d. Because of this, whenever we use diffraction grating, the distance between these will tend to be between the principal bright fringes will tend to be a lot larger than those we worked with whenever we had only two slits, because the distance between two slits tends to be a lot smaller. Because of this, in general, the small angle approximation won't be valid even for the very first bright fringe next to the center. Usually will be too far. We'll be over our 10 degrees mark. We'll have to work with the general equations and working with finding an angle and then putting it in the equation of y to find an actual position. Also, because we have such a distance between all the fringes, whenever we change the wavelength, here I'm working with red, the effect whenever I change the wavelength will be a lot larger. To compare how distances changed when I switch the wavelength here, compared to if I have a much larger distance. The effect, if you take for instance, if you look at, let's say, this one, the very first one on the left, check how its position changes. Not a whole lot, but if I do the same thing with this case, again, the very first one on the left, its position changes a lot more. So diffraction grating is a great tool whenever we want to differentiate several wavelengths in the same ray of light, which is why it is very useful in spectroscopy. In spectroscopy, you are using light emitted by some material of which you want to know the composition, and you want to the light you receive, depending on what transition the electron did inside of the atom, the wavelength emitted will change. So you usually receive a ray of light with with some wavelengths inside of it. They could be 2, 3, 5, and so on. And you want to differentiate them in order to be able to analyze it. So you want them to arrive on some type of screen at different position and with a large enough distance between them to be able to analyze them easily. This is where a diffraction grating comes in handy. You can just shine the light through it. Look on your paper on the screen you get after it, or in your instrument something. There is usually grating inside, and you'll be able to see the the bright spots at different places, which makes the analysis easier. So yeah, it would seem that having 1,000 slits will be a lot complicated, but it's as simple as having only two. Same thing. And this would bring us to the end of the material for the second exam. So for this, you actually have an example in your textbook, example 36.4. I also pointed out to you the exercises that were solved in the double-edged spell book. So I put it up on Leah. I took pictures of it and put it up there. So a total of 3 solved exercises in there. They are handwritten, so maybe not as clean as the other exercises I had sent you, but still they can help you get this sorted out. On this part, would you have some questions or comments? And also, so you can start typing them while I continue to talking a bit. Um, what I suggest, we could take a short break, and afterwards we could take a look at the formula sheet, have a talk over it, and afterwards maybe try an example. So what I do, I switch around my camera to have a top view to film. So some sheet of paper. We'll see how clear it gets. Also, the wiring is a bit finicky, so which is why I usually do not try this out. If the camera gets unplugged, it will be a bit of downtime for me to get this sorted out. My camera is my cell phone strapped to a lamp with rubber bands. So I'm trying. So I'm waiting for your questions and comments. Objections also, as always. Otherwise, short break. Let's say we could be back at 9:05. Just give me some time to set up something on my end, and then we'd be ready. So I'll see you in about 9 minutes, approximately. All right. Hi, everyone. So, what we could do? I set up a camera so I could point at a stack of paper. We could try an example on the combination of interference and diffraction. See how it goes. The camera I'm using has an autofocus, so when I'm moving my hand around, it might cause the focus of the camera to jump around. Uh, I'm not sure how to solve this at the moment. We'll try this out. If we see it doesn't work, we'll just move on to something else. And maybe once I have a second camera, hopefully next week, we'll have a better setup. So we could try our hands at exercise 36.22 on page 1212. So I read it aloud. I'll take out the important parameters, analyze it a bit, and then we'll try to solve it. So take a few seconds to take out your textbook if you don't have it nearby. Otherwise, I'll just read it out. In this exercise, we have a laser light of wavelength 500 nanometers. So this is the wavelength we're given. So again, tell me if I'm not writing large enough. I'll try my best. So 500 nanometers, which goes through two identical slits and produce an interference pattern on a screen located 90 centimeters from the slits. So this is the distance between the slits and the screen. So already we have some different units. I'll transfer all of them into meters. So nanometers are 10 to the power minus 9 meters. Centimeters, as you know, are 10 to the power minus 2 meters. The bright bands, so the location of the bright fringes due to interference, are 1 centimeter apart. So I'll write it down for now as delta y small m, since I'm talking about interference, is equal to, what was it again? 1 centimeter. And the third bright fringes on either side of the central maximum are missing in the pattern. So we do not see those at m equal 3 and m equal minus 3. And we want to find the width and the separation of the two slits. So this one is missing. And we want to find A and D. So what we'll do, first, we're given the distance between two bright fringes due to interference. Since we're given a constant, we'll suppose that we're working with the small angle approximation. When we're not working with it, the distance varies depending on the fringe we're looking at. But in this approximation, it is a constant. We're working, in the small approximation, the small angle approximation. We know that the position of a bright fringe is equal to its index times the distance between the slits and the screen times the wavelength over the distance between two edges between the two slits. So this is for a bright fringe. So if we're looking at two adjacent slits, So I'll take an index m for the one on the inside and +1 for the one that is more on the outside. So the distance between the two is the position of the one on the outside minus the position of the one on the inside. It is equal thus to the difference between their two expressions. So we'll have the index of the one on the outside, m+1. L is the same for both of them. So is the wavelength. And so is the distance between the two slits minus the one for the one the most on the inside. So basically, what we're looking at is we have our pattern. Here, we're looking at the distance, for instance, between this one and this one. So this one would be m+1, this one would be m at all. And here the third one is extinguished. But for now, so we want this distance. So working from this, here we have m L lambda over d plus L lambda over d minus m L lambda over d. These two cancel, and we have L lambda over d, which is equal to the distance between the two fringes, which was given to us at the beginning. So this is just over d. This is the other side of the camera, but this is over d. And so from this, we can find d as being L lambda over the distance that was given to us. So we'll find its value right away. So we were told that the distance L was 90 centimeters. Wavelength was 500 nanometers. And the distance between two fringes was 1 centimeter. So this cancels, and we have 90 times 500, some large number, which is equal to 45,000 times 10 to the minus 9 meters. I could also write it down as 45 times 10 to the minus 6 meters, which would be 45 micrometers. So this is equal to 10 to the power minus 6. All right, one down. Next, we'd like to find the width of each of these two slits. For this, we'll have to use the other information that was given to us, that the third bright fringe was extinguished. We could not see it. This means that it is exactly at the position of one of the dark fringes due to diffraction. So its intensity was forcefully dropped to 0. We'll suppose here that it was exactly the position of the first dark fringe due to diffraction. From the exercise, I have no real way of knowing which one it is, but if this was not the first case at which we had a missing bright fringe, it would probably have told us. So we'll suppose this is the first case that we encounter. So it should be at the first dark fringe. So from this, we'll work with the two equations we have in the small angle approximation. in the small angle approximation, otherwise, if we wanted to use a general case, in what follows, we'll compare the two positions y. We could also compare the two angular position theta. That will also work. So we have for diffraction, that the dark fringes are located at the values of y that respect this condition. In the case of interference, we have the equations for the bright fringes. And if we are told that the third bright fringe is extinguished by the first dark fringe due to diffraction, this means in math that the position of the first dark fringe due to diffraction is the same as the position of the third bright fringe due to interference. So their expressions have to be equal. We'll have 1 times lambda L over A is equal to 3 times lambda L over D. In both cases, we did not change the nature of the light. In fact, we have the same system. So the wavelength is the same. The distance between the slits and the screen is also the same. So these cancel. And we have, if I play with this around, so far we have that 1 over A is equal to 3 over D. So D is equal to 3 times A. So from this, A is equal to a third of D. And we found that D was 45 micrometers. So A is 50. And with this, we have our answer. So just from knowing the shape of the pattern that we got on a screen with light passing through a number of slits, we're able to deduce the characteristics of the system we used to create this pattern. So we know the width of these slits and the distance between the two of them. And something reassuring, they are less large than the distance that is between them. If we had found the inverse of it, if we had found that they were larger than the distance between the two of them, this would have been a bit strange, since they would, the two of them would in fact be one and single large slit, if that would have been the case. So A should always be smaller than D. The other case doesn't make any sense. So on this, you have questions, comments. How did it go? Did I tend to you to write too small? Did the camera autofocus was too distracting? How did it go? Went well, wasn't that bad actually. Okay, so if I give it a moment between each step, it's fine. Okay. Maybe a Sharpie would make it clearer when it was pretty clear. Okay, so the lines are a bit too thin. Okay, okay. I'll try to find something that might do the job for next week. Okay. All right. Thank you for the feedback. Yeah. Also, if I can, I'll try if I can put it maybe a bit closer to the sheet. So far, I just taped it to the tablet that is above. It is the best I can take care for now. I'll try to see if I can think of something else. So, thank you. Uh, Otherwise, that will bring us to the last part of today's class. So we'll do a short overview of the formula sheet. Have a short talk about it, the more qualitative parts, but will be centered around the formula sheet as we usually did. To the setup I have here, I won't be able to write on it, unlike what I did in the first exam, but you'll have everything I'll say recorded. So that's the best I can do in the given situation. So what we studied in the second part of the semester was optics. So we studied the behavior of light in a few different scenarios. In our first introduction, we stated that it traveled as an electromagnetic wave. So because of this, we could write if we wanted to. We never worked with it, but we could describe it with the same form as we used to describe other types of traveling waves in ropes, sound wave, and so on. We could, if we wanted to, use this form to write equations for the light, which would describe the electric field as it travels across space. Since it is a wave, it inherits the parameters we introduced earlier for waves. It has a frequency f. It has an angular frequency omega. It also has a period, capital T. And also, in terms of space, it has a wavelength, the distance between two locations which have uh, the same state, and it has a wave number as well, k. And these two sets of parameters, the one talking about space and the one talking about time, are related together through the speed of the wave. Again, if we have a wave, it has a given speed, v, which is given by the ratio of omega over k, or lambda over t, and we could also write it as such. If we are studying light, the speed of this wave is aptly named speed of light. In vacuum, we give a special name to this quantity, c, which has a given value of 3 times 10 to the power 8 meters per second. This is known in vacuum. But depending on the material, again, such as we had studied in the case of a rope, the speed of a wave on the rope depended on the linear mass of this rope. Again, the speed of light depends on in which material, in which medium it travels. To find the speed it travels in a given medium of index of refraction n, we take the speed of the wave in vacuum over the index of refraction, and we get the speed. This is also the actual definition of the index of refraction. It is just the ratio of the speed of light in vacuum compared to in the medium. It could also be written as the ratio of the wavelengths. So if it goes inside of a homogeneous material, light goes, at least, the rays go in a straight line. However, when they encounter a change in a medium, part of it will be reflected. So due with an angle described by the law of reflection. So the angle of incidence taken compared to the normal is equal to the angle of reflection, again compared to the normal. And part of it is transmitted in the new mediums. For instance, if you have an interface between air and water, part of it, if you send light starting from the air, part of it will be reflected back towards the air, and part of it will be transmitted, which we call refracted here, in the water with a different angle, described but not explained by the law of refraction, which links the index of refraction of the two mediums and the angle that the ray of light makes in each of these two mediums, always compared to the normal, never compared to the surface, always to the normal. The angle, because of this relation, tends to be greater in, not tends to, but is greater in the medium in which the index of refraction is the smallest. And if we study the case in which light started in the material which had the largest of the two indices of refraction, if the angle was equal or larger than a special angle we call the critical angle, we would have a total internal reflection, which means that none of the light would be transmitted to the second medium. All of it would be reflected back towards the first medium. This can happen, for instance, from water to air, because the index of refraction of water is greater than that of air. But it cannot occur in the inverse scenario, from air to water. This cannot occur ever. So we studied these cases, how rays of light behave whenever they change medium. And then we went on to study not only one ray at a time, but a few. And these rays were emitted by an object, and whenever they crossed path, or at least their extensions crossed path, we got an image. So we studied this with the case of mirrors and lenses. We, after taking a brief look at plane mirrors, in which case the image always was the same size as the object, was located at the same distance behind the interface as the object was before it, we took a look at spherical mirrors. We introduced these mirrors in an approximation. Sure, we treated them as spheres, but we only studied rays of light that were close to what we call the optic axis. And in which case, we approximated the sphere, the circle, as a parabola, which means we also had a focal point. Okay, the relation between r, the radius of curvature of the circle of the sphere, and f, the focal length, so the distance between the focal point and the mirror, was this one, that the focal length was half the radius of curvature, so the focal point was halfway between the center of the sphere and the mirror. We also introduced the relation between this focal length and the locations of the object compared to the mirror, and the image compared again to the mirror. These quantities, all three of them, had a sign convention. For F, it was positive for a concave mirror, negative for a convex one. S was positive if the object was on the same side of the mirror as the incident rays, and S prime was positive if it was on the same side as the reflected rays. Another way of seeing it was, if the image was formed by the crossing of the rays themselves, it was a real image, S prime was positive. If instead we had to take the extensions of the rays and these were the one crossing, we didn't have a real image. The rays themselves did not cross. We could put a screen there and get nothing. We had instead what we call a virtual image with an S prime that was negative. So an image that we cannot get directly on a screen, but we can combine with other optical instruments to get an image in the end. This is what the eye does. We can see a virtual image because the eye is another optical instrument which can take this image and in the end still create something on the retina of your eye. Was introduced M, which was the transverse magnification. So how large the image is compared to the object. It also carries the meaning of the orientation of the image compared to the object. Yi is the height of the image, Yo that of the object, with each a sign, positive if they are above the optic axis, negative if they are below. So if these two have the same sign, they have the same orientation, M is positive, the image has the same orientation as the object. If these two have do not have the same sign, M will be negative. So a negative M is an indication that the image is upside down compared to the object. And we could also find this using S and S prime, again, using the sign convention we had introduced. These expressions we first introduced for mirrors, but they still worked in the case of lenses. These two, not the middle one, but this one and this one, we also worked with in the case of thin lenses, again with spherical interfaces we treated as parabolas, with a very similar type of sign convention. F was positive for a converging lens, a lens that makes the rays converge towards a given point. Negative for a diverging lens, which made, as the name implies, the rays diverge. And S and S prime, again, the similar sign convention. S was positive for a real object, meaning the incident rays were on the same side as the object. This is the only case we get when we have a single lens or a single mirror. We could also get a virtual object, but only in the very specific case when we had more than one optical instrument, so more than one lens or more than one mirror. Otherwise, this is impossible. And S prime, again, for a real image, it was positive in the case where the image was formed by the crossing of the rays themselves, meaning the rays, after going through the lens, were on the same side as the image. If instead the image was made by the crossing of the extensions of the rays, it was a virtual image. And we had the same thing here for the magnification. In the case where we had not only one but two lenses, we could find the total magnification of the two lens system by taking the product of the magnification created by the first lens times that created by the second. And the total was just the product of the two. We also introduced the power of lens as the inverse of its focal length. So the focal length was the focal point, was the location at which parallel rays came and crossed. So the closer this point is towards the lens, the more the rays converge fast. So the more powerful the lens is, the more it alters the path of the rays of light. So P is the power measured in diopters. And whenever we had two lenses very, very close to each other, the total power of the two lens system was given by the sum of the powers of each lens taken individually. This we took to study the eye and how to correct its vision. So the eye is an optical instrument with a lens inside of it that can adapt its focal length by changing its shape, the lens of the eye, as its name implies. So whenever you are looking at a close by object, the muscles around the lens tense to make the lens more curved, so it can better alter the path of the rays. Whenever looking far away, they tend to relax to make the lens flatter, to less alter the path of the rays. And whenever we wanted to correct someone's visions, we could add the power the of the lens we want to put in front of the eye plus that of the eye itself to get the total power of the lens of the glasses of the contact lenses plus that of the eye. To solve this, you can go back on the examples we did, but the one of the contact lens we left as is because this is what we wanted to find. The one of the eye we played around with the power being the inverse of the focal length, and the inverse of the focal length being 1 over the position of the object plus 1 over the position of the image. To rewrite this, the image was always created on the retina, so this was always the length of the eye, whether we were taking the eye alone or the combined system, the eye plus the contact lens. And this was how far away the object was from the eye. Here was the position at which the eye alone could see clearly. Here was the position at which we wanted the eye to see clearly, so the position at which the vision would be corrected. And we use this to find the power of the lens. And next is what we studied in after the break. So we took a look at light, not as only a bunch of rays, but as waves, which could interfere. So we introduced the condition for constructive interference and destructive interference as termed in terms of wavelength of the two waves interfering. Then we applied this to the case of two slits separated by a small distance. We found the path difference as a function of d, the difference between the distance between the two lenses, between the two slits, and the angle at which we are looking. And through geometry, we found an expression of the position on the screen as a function of the distance between the slits in the screen and the angle. Combining this, and this, we found an expression of the positions in the small angle approximation of the bright fringes, and by combining this, and this, found an expression of the position of the dark fringes in the small angle approximation. We then went on to study the effect of diffraction of the width of a slit. We had the angular positions of the dark fringes given by this expression with the index being integer but not 0. And again, by combining this and this, found an expression of the position of the dark fringes in the small angle approximation. Whenever we have two slits of finite width, it has a combination of the fringes created by interference, but with the intensity modulated by diffraction. And whenever we have a lot of slits, which we call a grating, what we see are bright spots created by the interference of all of the slits together. So we have the same condition as when we have two slits, and we could still use this, and this to find out the locations of the bright fringes. And at the bottom, you have a bunch of expressions, some useful, some useless, some indices of refraction that were useful quite often, and a reminder of some units how to transfer into meters. And at the bottom, sorry, I missed that out. The two graphs I introduced that represent the relation in the case of a concave mirror or converging lens, so in blue, and for a diverging lens or convex mirror, again in blue, which could give you the relation between the characteristics of an object and the image it creates. And that would bring me to the end of the summary. So all of this you will have on the day of the exam. This is what I will hand you to solve the exercises and the short questions. That would be pretty much all on my end. Would you have something to add on this? Some questions or comments? Anything? While you type this. Tomorrow, what we could do, we could well, if you want to, I'd be available on Zoom to answer questions. We could also do examples together if you'd like, but I would not um, structure it really as a lecture, but more as time to work on exercises, either together or on your own, where I answer questions, whichever you would prefer. Yeah, tomorrow would be on Zoom instead. Yeah. It wouldn't really be a stream since I do not have new material to show tomorrow. I don't see really a point to structure it as a stream. So really, I'd see more as a question and answer session instead. I sent you by Mio the link to the room, also the password a few minutes afterwards. But yeah, so I think it would be better for to do example exercises this way instead. Yes, exactly, Kimberly. The first version of the formula sheet I had sent was the one of you would have used normally in a normal session. We would have seen a bit more material. So in the one I showed, I cut out the formulas which we won't use. So these I showed are the only ones you will need. The ones that are on your version that are not on the one I showed now are not necessary. You can find the updated version up on layout. Otherwise, I think I'd call it a day. Well, for today's class, I'll see you. Well, if you want tomorrow at 8, I'll be on Zoom to do some exercises with you. So until then, have a nice day, and I'll see you hopefully tomorrow. See you.